Hi everybody. So today's live, I am going to do section 7.2, which is two variable linear systems. So I'm going to start by sharing my screen, and then I'm going to go through my examples and explain. So let me get that started. All right, let me move this little thing away. There we go. Okay, so 7.2 covers two variable linear systems. So the objectives that this section covers are to use the method of elimination to solve systems of linear equations in two variables, to interpret graphically the numbers of solutions of systems of linear equations in two variables, and then to use systems of linear equations in two variables to model and solve real-life problems. So we're going to start with the definition of elimination. So, or basically what it is. It doesn't really have a definition, but what you do. So the goal of the elimination process for solving is to get equations that, when they are added together, they eliminate one of the variables. So if you have two variables, you want to eliminate either x or y. You can do elimination with three variables. You would have to eliminate, if you have x, y, and z, you want to eliminate either x or y or z, and then you'll have to do elimination a second time so that you get down to one variable. So we do this by using the following properties. These are the two properties of algebra. We've got the multiplication property of equality, which says that you can multiply both sides of an equation by the same number or the same thing. And then we have the addition property of equality, which means that you can add the same thing to both sides. And we're going to use that property to basically add the same equation to both sides, essentially. So that's basically the thing. So when you have a two variable system, which is the best way to use an elimination, these are the steps. It's worded a little differently than the text. I try to put it in words that make sense to me. So first, you need to make sure that each equation has x and y on the same side. So if they're not on the same side, you need to rearrange them so that they are on the same side. And you may not have x or y, you may have other variables, but they need to be all on the same side. Once you've done that, then you want to pick which variable you want to eliminate or disappear, whether it's x or y. Once you've decided that, you want to take a look at the coefficients for that variable. So if you have like a 2x and a 3x, and you want to get rid of x, you're going to look at the 2 and the 3, and you're going to find the least common multiple of those coefficients. So for 2 and 3, that would be 6. So your goal is then to make those variables, the variable x, have a coefficient of 6 instead of 2 or instead of 3. And so you do that by multiplying each side of the equation by the number that would make it your least common multiple. So if you have an equation and you're trying to get 2x to become 6x, you'd be multiplying that equation by 3. If you had 3x and you're trying to get 6x, you'd be multiplying it by 2. And then you want to make sure that they have opposite signs. So you can multiply one of those equations by -1 so that you have a 6x and a -6x. You need to have opposite signs because we're going to be adding the equations together, and then that causes them to eliminate because they will add to 0. So you want to get them to have the least common multiple, but they need to be opposite signs. Once you've done that, then you add the equations together, and we do this vertically because it's really easy to just add going down. And what will happen is that one of them adds to 0. So that leaves you with the one variable remaining, and so then you just solve. So if I eliminated x, then I'd be solving for y. And once you have your variable for y, or your value for y, then you plug it in to one of the equations that you started with to find the other variable x. So that's the basic process. So I have an example here, and I picked one with decimals because there's a nice little trick about decimals, and I usually do the elimination process, or I don't do the process twice, but I multiply them twice, just first to eliminate decimals and then to do the elimination process. So we have here 0.5x minus 0.3y equals 6.5, and then 0.7x plus 0.2y equals 6. So I just count how many decimal places I have. So here I have 1 decimal place. So I'm going to multiply everything by 10 to get rid of that decimal place. So if you had 2 decimal places, you'd be multiplying by 100. So, getting my pen out, I'm going to multiply each equation by 10. And so that's how I indicate that I'm multiplying the equations by 10. And so I'm going to just move that over. And so I'm essentially 0.5 times 10 is moving the decimal 1 place. So this is going to give me 5x. Then I get minus 3y equals 65. And then 7x plus 2y equals 60. So now that is my new system. So now that I've got a system with whole numbers, which is a lot easier to work with, and now I want to do the elimination process. And so I need to decide, do I want to get rid of x or do I want to get rid of y? So you can do it either way. There's little things that you can look for. I usually, if I have 2 that are the opposite sign already, then I'll tend to try to eliminate that one. Like in this case, because the y already have opposite signs, I would probably go with that method. I also try to pick ones where I have to multiply by smaller numbers, just because it makes it a lot easier to multiply. So if I was trying to get rid of the x's, I'd have to multiply the first equation by 7 and the second equation by 5 to get a common coefficient of 35, because that's the least common multiple between 5 and 7. For the y's, I only need to multiply by 2 and 3 because their least common multiple is 6. So that's a lot smaller. So looking at this, I'd be more inclined to eliminate the y because it has opposite signs, and I need a smaller number when I'm multiplying. So it just makes things a little easier. So since they're the opposite sign, I don't have to worry about a -1 deal, but I'm going to multiply the first equation by 2 so I can get a -6 in front of my y. So I'm going to, again, just write that I'm multiplying that by 2. And then the second equation, I'm going to multiply that one by 3 so that I get a +6. So again, I'm going to just move over. And you can do these vertically if you want. I tend to go to the right when I'm doing these. It just kind of, I don't know, just makes it easier when I see how my equations are progressing. So when I multiply the first equation by 10, you do have to multiply everything, or not by 10, by 2 to get 10. I get 10x minus 6y. And then you do also have to multiply the 65 by 2, and a lot of people tend to forget that. And so if that's something that you tend to forget, you can also write the number you're multiplying by on the right side so that you don't forget that. So 65 by 2 gives me 130. So I'm going to have that equal to 130. And then in the second equation, I get 3 times 7, so that's 21x. Then I get plus 6y. And then 60 times 3 will give me 180. So now that's my new system. Now I'm going to just rewrite it. I have more than enough space here, but I'm going to just rewrite it so that I'm not solving all of my stuff on the far right of the screen. So now this is my new system that I am working with. I have 10x minus 6y equals 13. And then 21x plus 6y equals 180. So now my y's have the same coefficient opposite sides, so when I add these, the y will be eliminated. So I'm going to add these equations together. So I'm going to just draw my line, and then I add them going down. So if you want, you can just put a little plus there. So when I add the x's, 10 plus 21, I get 31. And then I get a -6 plus 6, that's 0. And then 130, it's a good thing I caught that. 130 plus 180, that gives me 310. So now I'm just solving for x, and you can see that now it's pretty simple to solve for x. All I need to do is divide both sides by 31, and then this gives me 10 for x. So now that I've plugged in, or now that I've solved for x, I need to find y. So generally you want to plug into the original equation, but the original equation is kind of nasty because we have decimals. And the nice thing is that if you want, you can plug it into one of the other equations. These are all equivalent equations. So all the equations I created on the very top, let me just kind of highlight them. So everything above this yellow line, these are all equivalent equations. They're all, they'll give you the same solution because I use the multiplication property of equality. And because I multiplied the same thing on both sides, I created an equivalent equation. So these are equivalent systems. They'll give you the same solution. So instead of plugging in my x into the equation with the decimals, I could choose to plug it into the one that I have without the decimals, like the system with the 5x minus 3y equals 65, or the 7x plus 2y equals 60. So I can choose either one to plug it in, and I look at it, I try to see which one's going to be easier. So if I plug it into the first equation, I'll have to deal with a -3 in front of y. And people like to deal with positives, so I'm going to plug it into the second equation because then I don't have to deal with a negative coefficient. The amount of work is the same, it's just, people make mistakes when they deal with negatives, so it's just easier to avoid that. So I'm going to replace x in the 7x plus 2y equals 60 equation with my value of 10. So that's going to be 7 times 10 plus 2y equals 60. So now I'm going to solve for y. So I have 70 plus 2y equals 60. And now I'm going to subtract 70 from both sides so I can solve for y. So that gives me 2y equals -10. Now I'm going to deal with the negative here anyway, but a lot of people tend to forget the negative when they have a negative coefficient and they're doing the division. So this just kind of eliminates possible errors. So I'm going to divide both sides by 2. And this gives me y is equal to -5. So now it's good practice to check your answer, and you can do that by plugging in your x and y into the other equation. So I used the 7x plus 2y equation, so if I plug in those values into my 5x minus 3y, that is a good way to check to make sure I did everything correctly. So I'm going to plug in both the x and the y. So 5 times 10 is 50. -3 times -5 is a positive 15. And you can see 50 plus 15 gives you 65. So because it worked in that other equation, that means that the solution is correct. And so we give our solution as an ordered pair. So it is 10, comma, -5. You need to make sure that you have it as x, comma, y. So that's an example of the elimination process. It's pretty straightforward. The hardest part is probably figuring out what you need to multiply the equations by. But once you have the equation in such a way that it's going to eliminate, from there it's not too bad. So I mentioned that each equation that I created when I multiplied was an equivalent system. So, like I said, equivalent systems produce the same solutions even if they do look different. And so you can create equivalent systems by either interchanging two equations, so that means maybe flipping which one's on top. You can multiply an equation by a non-zero constant. We multiply both equations. That still has an equivalent system. You can also create one by adding a multiple of one equation to another equation and then replacing one of the equations. So you can also do this. So an example would be if I added the two equations together, and then that result, which still had an x and y, adding them before they eliminate, I replaced one of them with that equation. And then you have an equivalent system. So, and these are all using the properties of equality. which are one of our mathematical rules that we follow when we're solving in order to make sure that our solutions are all the same. That, whatever you started with, you can still have the same solution, even if you manipulate the equation. So the graphical interpretation of solutions to linear systems. So you could have exactly one solution, which is what happened on that example that I did. And that's where your lines intersect at a single point. So if you were to graph your equations, they would just have an intersection somewhere. Your graph might look different, but there is going to be some point where they cross, and that is your solution. And so if we're dealing with linear systems and you have lines, that means that the slopes are not going to be the same. Now you could get infinite many solutions, where that ends up being where if you graphed your two lines, they are identical lines, and so you really only see one line. We write those solutions in a very specific way. Our textbook writes them as an ordered pair with A and f of A. Where instead of x, you just write a, and then you have your equation and you solve one of them for y, but instead of x, you use a. Some other textbooks also write it in like a set builder form where they might have x where and then they put in the equation. So that's an alternate way, but our textbook puts them in ordered pairs. And then your third option for a solution is that you have no solution at all, and that is when they are parallel. So if they're parallel lines, trust me that those are attempting to be parallel. They're not perfect lines. But if they're parallel, then they don't intersect anywhere, which means that there is no solution. So parallel lines have the same slope. Now, in infinite many solutions, those lines will also have the same slope, but what's different is the y-intercepts. For infinite many solutions, the y-intercepts will be the same. For no solution, they're going to have different y-intercepts. So if you have something with no solution, we call it inconsistent. And the opposite of inconsistent is consistent. And so having one solution or infinite many solutions is consistent. It basically means, yes, there is a solution. Even if there's more than one solution, it still has a solution, so that's consistent versus inconsistent. So a great way to check your answer is to graph. You can graph and then you can see, okay, did I get an intersection point? Does it match with what I solved for? Or, oh, are these, parallel lines? So I have here another example that we're going to solve. So we have a system, negative 7x plus 6y equals negative 4, and then 14x minus 12y equals 8. So we're looking at this, we want to eliminate either the x or the y. And when I look at these, I just say, oh, well, that first equation, if I multiply it by 2, then I'm going to get the numbers in the second equation. So that's what I'm going to do. I'm going to multiply by 2. And I'm going to indicate this on both sides so it just doesn't get too confusing. Just an alternate way to show. So when I multiply everything by 2, I get negative 14x plus 12y equals negative 8. And then 14x minus 12y equals 8. So you may notice here that the coefficients are the same, they're opposite signs. This is special. So I'm going to move underneath so I can show the addition of these. So I have negative 14x plus 12y equals negative 8. 14x minus 12y equals 8. So when I add these equations together, negative 14 plus 14 is 0. 12 minus 12 is 0. So everything on the left cancels. So I'm going to just write 0. On the right, we have negative 8 plus 8. That is also 0. So we got 0 equals 0. When you get that, when you get 0 equals 0 or 2 equals 2 or anything, some true statement, so I'm going to indicate this as a true statement, that means that you have infinite solutions. So we have infinite solutions. These equations are identical. And you can see that because if I multiply the first equation by -2, I get the same equation, the second equation. If I solve both of these for y, you'd get the same exact equation. So when we have something that has infinite solutions, we need to write our solution with our ordered pair. So I'm going to take one of the equations and I'm going to solve it for y. So I'm going to just start with the first equation just because it has smaller numbers. And so I need to solve this equation for y. So I'm going to start by adding 7x to both sides. So it gives me 6y equals 7x minus 4. I'm solving for y, so I am going to divide everything by 6. So this gives me y equals 7/6 x, and then 4/6 reduces to 2/3, so it's going to be minus 2/3. So that is our equation for a line. If you solved the second equation, you would get the same thing. So we write our ordered pair as a, and then we take what y is equal to, and everywhere we see x, we just write it as a. So you would have a, comma, 7/6 a minus 2/3. And you could put a little note where a is a real number. Basically, you can put any number in for a, and that will give you an ordered pair. They don't use x and y, just so that you don't think the solution is an equation. The solution isn't an equation, it's an ordered pair, but there are infinite many ordered pairs. So that's an example of what happens when you solve and you end up with infinite solutions and how you would write that. So applications. You know that you have a word problem where you're going to have to solve a system of linear equations when you have more than one unknown. So you have to think about, what do I not know that I'm trying to find? You have more than one. And there are 2 or more equations or conditions to be satisfied. So if those things are true, that's going to tell you immediately this is going to be a system. And so I need to write multiple equations, and I'm going to have multiple unknowns that I'm solving for. There are some basic types of linear system word problems. So you have distance or rate or time types of problems. A lot of those are with like airplanes. If you're flying one way and with some speed, and then you're flying the other way and it's a different speed and you have wind involved. That happens a lot with rowing or biking. Maybe someone's biking, someone else is in a car. You know, those train problems, those kind of things, those are often end up with linear systems when there's more than one unknown, usually speed of the 2 different vehicles, or speed of like a current in a boat or an airplane and the wind. Mixture problems, those happen a lot in chemistry, where you're mixing 2 things together. You're mixing like acid and a base, and one's 20%, one's 30% or something like that. Antifreeze is a mixture of like water and then whatever the chemical is in antifreeze. Gasoline is a mixture problem. So anything where you're mixing things together. Sometimes you're creating mixtures with like mixtures in nuts. Maybe you have almonds, some sort of, and then I don't know, walnuts or something, and you're mixing them together, and you have different prices for each one. Those can be considered mixture problems. Those can also fall under the number of items or the money problems. Because it depends on what you're mixing together. Are you looking at the price per pound, or are you trying to figure out how many pounds you need of each, those sort of things. Mixtures tend to be mostly for percentages. Equilibrium or break-even problems, those tend to happen a lot with money type of problems, where you're trying to find, when are you going to break even? Say you have revenue and cost, or you want to know when your 2 different salaries are equal, so you can figure out which one would give you more money, or when you would need to have more where they, you know, where they equal. How many hours do I need to work to make this much money? Those are kind of some break-even problems. Number of items problems, like you have 2 apples and 5 oranges and they cost this much money, and then 5 apples and 7 oranges cost this much. How much does each one cost by itself? Or how many do I need to buy in order if I have this much money? Or how many can I buy if I have this much money? Something like that. Those are number of items problems. Sometimes you'll see it with the number of tickets sold, this many children's tickets, this many adults tickets, how much is each ticket worth? Money problems could be investments. You invest this at a certain percent and another one at a different percent. And that is similar to the mixture problems because they're dealing with percents. And if you notice, or if you do a few of those problems, you'll see that they're set up pretty much exactly the same. Price of items. This costs this, like an apple costs this much, an orange costs this much. Those are kind of similar to the number of items problems because they usually are also trying to find out how many you need of each. So those are set up very similarly. Total of each, very similar. So anything that involves dollars usually is like some of the other problems. Same thing if you are doing things with the weights. They usually fall into a mixture type problem or a number of item problems. Sometimes the money ones involve break-even problems. But I call them money problems because they involve money in some sense. So here's an example of a word problem. 2 cheeseburgers and 1 small order of fries contain a total of 1420 calories. 3 cheeseburgers and 2 small orders of fries contain a total of 2,290 calories. Find the caloric content of each item. So it says each item, so that tells us we have more than one unknown. And it says find the caloric content. So we want to know how many calories are in each item. So those are our unknowns. Those are what we're looking for. And so your first step is you need to identify your variables. This is really important if someone's reading your work because if you just use X and Y without labeling, is the X the cheeseburger or the fries? You need to make sure you label them so that when you get to the answer, you know which one is which, because I've seen people get confused. They forget which one is which, and then it also helps communicate to me so I know what you label as each. So, and I like to use variables that make sense. So we're going to let C equal the calories in a cheeseburger. So that's one item. And then let's say F is the calories in fries. We could, if we want to be very specific, we should say in a small order of fries. So that makes it very explicit what your variables are. So that way it's easy when you're solving so you know what you just found. We call this defining variables, and it's your first step in any word problem is to define your variables. The second step is to come up with your equations. So here, because they're telling us how many we have, how many cheeseburgers we have, how many fries we have, this is considered a number of items problem because they're telling us how many we have. And that one is, it's actually quite simple to turn into an equation because you're just literally translating the sentences. So we have 2 cheeseburgers. So I'm going to just use C, the calories in a cheeseburger, 2 times the cheeseburgers. And so we're adding in 1 order of fries, so 1F. And the number of calories here is 1,420. If you think of it with the units, it makes sense. The number of calories in a cheeseburger multiplied by 2 because we have 2 cheeseburgers. So that gives me the total calories in cheeseburgers. And then 1 times F, we're adding in the calories from 1 order of fries. And so that gives us our total calories. So then you do the same thing with your next sentence. 3 cheeseburgers and 2 orders of fries is 2,290. So once you get your equations, you need to indicate that it's a system using your curly braces. So that tells me, okay, that is my system of equations. Very clearly, that's the system that I'm solving. So now I want to solve this system for each variable. So looking at my numbers, I can multiply the first equation by a -2. That would give me my fries, the f's, to have opposite coefficients, one positive, one negative, and there'll be 2. And then I only have to multiply one equation. So if an alternate way to show your work is you can say mult by -2, just to tell me what you did, instead of like doing what I was doing before and showing it. And so you can multiply by everything by -2, so that gives us -4c minus 2f. And then you need to remember to also multiply the 1420 by -2, and that gives us -2840. I have 3c plus 2f equals 2290. So now I'm going to add these equations together. So I have a -4c plus 3c, so that's -1c. -2 plus 2 is 0. And then -2840 plus 2290, -550. So we have -1c equals -550, so I just need to multiply or divide both sides by -1. So we get a cheeseburger. The calories in the cheeseburger is 550. So now that I've found that out, I need to know how many is a small order of fries, because I need to go back to the question. The question says, find the caloric content of each item. So I need to find for both. So I'm going to plug it into my first equation because I have one f, so that's going to make it a lot easier to solve. So I have 2c plus f equals 1420. And I replace c, so that's going to be 2 times 550 plus f equals 1420. So 2 times 550 is 1100 plus f is 1420. So now I'm going to subtract so that I can solve for f. And I could do this in my head, but I just like to use a calculator just to verify. 320. Okay, so now I have c is 550, f is 320. Now this is a word problem, so you don't give your answer as an ordered pair, because an ordered pair doesn't really make sense in a word problem. For a word problem, you want to give your answer in a sentence, because we have words. So, and you need to be very explicit. So your answer would be, there are 550 calories in a cheeseburger, and 320 calories in a small order of fries. So for word problems, your answer should be in sentences. They should be in context, making it clear what you solve for. You want to include units. In this case, the units are calories. You want to be very specific. So that's basically how you use elimination, and then an example of how you can use elimination to solve the word problem. Hopefully this was helpful. I recommend watching some of my other videos. I have videos on solving systems by substitution and by graphing. I also have a couple videos on solving systems with word problems. It's a video called Modeling with Systems, so that's a good one to check out if you want to see more examples of word problems. In that video, I'm not showing the solving process, more the setup process, so that you learn how to set up these types of problems. You can kind of learn the tips and tricks for when you're doing these problems in real life. So if you have any questions, you know how to reach me, and I hope you guys have a great day. Bye.